most bandwidth of any fiber, but again, there's certain places you don't need to use it. Has less bandwidth than single mode for multi-mode, but it's still much better than a lot of copper. Common wavelengths for single mode are 1310 nanometer and 1550 nanometer lasers. And on single mode or on multi-mode, the common wavelengths are 850 nanometer, which is usually a VCSEL, and 1300 nanometer, which is an LED. This 1300 and 1310 are not the same thing. They're not interchangeable. You can't interchange. So I'm going to skip over this middle bandwidth. It just kind of shows that 1300 nanometer, everything is the same as 500 megahertz per kilometer. And as you go up to the different, it increases from 62.5 micron to the regular 50. Then there's something called OM3, increases a little more, and then the newest fiber is OM4, increases a little more. Let me give you this illustration of bandwidth. Bandwidth is a very difficult concept to get people to understand. It's hard to imagine what bandwidth is. Hartley's law states that the maximum data rate of a data link is proportional to its bandwidth in hertz. Everybody understands, right? So I've seen a highway illustrator, or people talk about the highway illustration, and I've taken that information and tried to illustrate it here. It's not perfect, but it gets the point across. So you have a 2-lane highway, which is, we'll call that low bandwidth, and we'll call the 3-lane highway over here high bandwidth. So if I put 12 cars on this 2-lane, everybody has to travel at the same speed. There's no room for variation here, right? Nobody can pass, nobody can speed up, slow down, whatever. So we're pretty much at capacity here at 48 people. I have an asterisk here because later I'll prove that wrong. But if I take those same 12 cars and put them over here on the high bandwidth area, notice that I have extra space in here. People can speed up, slow down, they can vary their rate, and I've actually got space here that I can put more capacity. So let's say that this is data. This is megabits or gigabits or whatever. I could actually fit more on there, so I'm going to put more on there. So I put 12 more people in there, or 12 more cars in there, 4 people per car. The conversation or mode, let's just say, or data is a person. So I've pretty much packed that in there. No longer can they speed up and slow down. Can't add extra cars in there. You'd think that was probably pretty much a capacity, right? Well, I liken all this to copper. Over the years, they've increased it and increased it again. Think we're at capacity? Let's bring in fiber. Fiber's the bus. You pack that 3-lane highway with buses, you can fit a heck of a lot more people on buses on that road than you can in cars on that road. So we've increased the bandwidth again. So in layman's terms, bandwidth is the carrying capacity of a transportation medium. So it doesn't matter if it's a car, a piece of copper, a piece of fiber, even a speaker, a microphone. I mean, anything has to be able to carry something without distortion or loss. Some different modes for optical fiber. I mentioned earlier, I told you the annular rings, and I said we would talk about gradient index. We started out with step index, which was the original multi-mode fiber, and that was just basically a solid core and a cladding. So you had your input pulse here, and all your modes come through. Notice they all stop at different, or they all have to travel at different speeds here, and end at different times. So what happens there is you get pulse spreading. Each of these pulses is slowed down a little bit or sped up, so you get pulse spreading. And you also lose amplitude. So that's your input pulse, that's your output pulse. Is that what you really want to see? Probably not. So if we go on to gradient index fiber has those annular rings, and as you see, the annular rings help keep everything confined at the same speed. So if I was to cut off right here, all of those modes are ending exactly the same time. There is still a little bit of pulse spreading. That's due to impurities in glass and other things like that. But I'd much rather have this little bit of spreading here and there's a little loss in amplitude than what happened here. Now, single mode is step index. So you can't just say in fiber optics there's no such thing as step index anymore, because single mode is all step index. Because it's a single mode, you don't really need to control multiple modes. So your input line, your input signal there, your output signal, it's relatively the same. Again, impurities of glass cause a little bit of pulse spreading here, but you don't lose a whole lot of amplitude. There are things, it's dispersion. Dispersion means to break up and go away. So some things that happen with fiber optics on multi-mode fiber, especially multi-mode step index fiber, if I put an input pulse, I have three signals going in. These three conversations go through here. And in step index, they all arrive at different times. You have that pulse spreading I talked about. See what happens here? You have these overlaps of your three signals. You can't tell the difference between whether it's a sine wave or whether it's a digital signal. You can't tell the difference between a 1 and a 0 or anything like that. It's a bunch of mush. So you have to keep sending and have repeat, repeat, repeat until the receiver can interpret the data properly. On signal mode step index, you have something called chromatic dispersion, which your wavelength actually can break up. So let's say this was 1310 nanometer, and for whatever reason inside this glass, whether it's impurities or whether it was most likely it's a laser source that's causing this, that the wavelengths kind of break apart. They kind of separate from 1310, maybe 1310.5, 0.7, 1311, whatever. And you get this chromatic dispersion where your output pulse has a mix of a whole bunch of different wavelengths and might have part of the signal in this, part of the signal in that. It happens. That's something to be concerned about. Then there's something called rayless scattering. There's these impurities that are in the glass that are made into the glass, and they need to be there. The glass that we're using now, if you're out on a boat and you put it down to the bottom of the ocean, it's so clear that you can see to the bottom of the ocean through that piece of glass. It's very clear. It's not perfectly clear. These impurities are in there for a reason, and that's when you use an OTDR or any other type of test equipment that's going to tell you the length of your cable. I mean, if you run something across the Pacific Ocean, do you actually want to stand there and step it off? You can't walk across water. But you can use an OTDR to check that. Well, these imperfections here are what allow the light of an OTDR and other equipment to bounce back. And so they can get a gauge and say, okay, I'm going out 10 meters, 100 meters, 10 kilometers, 100 kilometers, whatever it is. So they're there. But the problem is in regular communication, depending on the size of those impurities, you get something called rayless scattering, where the light goes in and it hits a particle. Sometimes it'll hit like this particle here. It drove right through it. It said, I can go right through that particle and out the other end. Not a big deal. But sometimes the wavelength comes in, it hits that particle and scatters in any given direction. It's not a controlled direction. And that's a portion of your light, portion of your data that's lost. It's not as big a deal as a big hunk of dirt on it, but it is something to be concerned about. Some different things here, we don't know the maximum, it's never been proven. You guys go through fiber, who knows, maybe one of you guys someday will figure out the next longest run of fiber that can be done, single mode. But the maximum distance for running single mode is unknown. I mean, like I said, we ran 40 kilometers and still was no problem. Multi-mode, basically 62.5 micron, you're limited at, this is 10 gigabit. You're limited to about 33 meters. 50 micron gets about 82 meters. This is OM3, goes up to 300 meters. And then there's something new called OM4. I'm not sure what happened in my text here, but that can get you out to 550 meters at 10 gig, which 10 gigs, depending on your market, the market I'm in, 10 gigs, like, that's the goal, that's the big thing. Another part of our company, 100 gig, 40 gig, 100 gig, 120 gig, even much more than that. We have customers in our O&M world that use a lot more than that. But there is talk in the premise wiring about 4800 gig. I'm not going to cover that today. Distance limitations. Multimedia, you can go 2,000 meters for 155 megabits per second, but you can't imagine anybody here wants to do anything that slow. For 1 gig, you get 550 meters. 10 gig, I think I mentioned, you can do, for OM3, you can do 300 meters. So think here, there are two multi-modes. Basically, they're compatible with each other. I'm going to breeze through a couple of these slides here just because I know we're getting tight on time. But the idea is, there are questions, sometimes people try to mate, they're multi-mode, they try to mate these two together, the 50 micron and 62.5 micron. Well, what's the problem with that? So I'm going to breeze through some of these questions. I have a series of